going to focus on experimental probability. Probability that is based on repeated trials of an experiment is called experimental probability. We have previously talked about theoretical probability. Theoretical probability is what you expect to happen. And experimental probability is based on things that have actually happened. The formula that we're going to use to calculate experimental probability is the probability of the event occurring equals the number of times the event actually occurs out of the total number of trials. So if we were to look at this, if 13 out of 20 emails in your inbox are junk emails, what is the experimental probability that your next email is junk? So we've had 20 trials, so to speak, because 20 emails are in your inbox. Out of those 20, 13 of them are the junk emails, so the number of times the event occurs. We put 13 because it asks, what is the experimental probability that your next email is junk? So junk is the number of times that particular event occurs, which is 13. So 13 out of 20 is the experimental probability because this is what has actually happened. So we can say that the probability that your next email will be junk is 13/20ths, or 65%. This makes sense that it's going to be more likely than not because more than 50% of your emails are junk emails. We can use experimental probability to help us make predictions, just like we did, kind of, with the emails. If it rains 2 out of the last 12 days in March, then if this trend continues, how many rainy days would you expect in April? So we would say that the probability of the rain, well, what actually happened out of our 12 trial days is that it rained 2 days. So this is what actually happened out of the total number of trials. And trials would be days in this aspect. So 2 days of rain out of 12 total days. We would simplify that down as much as we can to say that the probability of rain is going to be about 1/6. So to make a prediction, there are 2 methods that you can use. You can use your experimental probability and multiply by the total number of days in April, or you can set up a ratio box saying the days you expect to have rain out of the total number of days, making sure to set up your ratio box as rain over total. So if I were to multiply, I'd say the probability of rain is 1/6 of the days. So 1/6 of the total days in April, well, there are 30 days in April. If I multiply 1/6 by 30, I would then say 1/6 times 30 over 1, and that would give me 30 over 6, which is equal to 5. So I can safely say that I would predict that 5 days in April would have rain based on what I observed the last 12 days in March. That was my experiment. Okay? So then in my ratio box, if I set it up as days with rain out of total days, I can use 1/6, or I could also go back to my original measurement because they're equivalent and say 2/12.
Mrs. Garcia, if you would come to the front office.
If there are 2 days of rain out of 12 total days, and I don't know how many days of rain I expect out of the 30 total days in April, if I look for my multiplicative relationships, I know that 2 times 6 is 12, but I'm interested in getting back to R. So I can just do the inverse of multiplication, which we know is division. 30 divided by 6 should get me R because 12 divided by 6 is 2. So 30 divided by 6 is in fact 5. If you're more comfortable doing both methods and making sure they check with each other, that might be a really good idea. But either way, you get the correct answer. And that is your prediction of 5 days of rain in April. Here's another example of making predictions using our experimental probability. At a clothing company, an inspector finds 5 defective pairs in a shipment of 200 jeans. What is the experimental probability of a pair of jeans being defective? Well, the probability that they will be defective is, well, 5, which is what actually occurred, out of 200. So I would say, well, that's 5 out of 200. If I wanted to simplify that, I could say that that's 1 out of 40 pairs. And 1/40th is going to be about 2.5%. Okay? So the probability would be 1/40th. If we think about that on the spectrum of likelihood that you're going to have a defective pair of genes, 1/40th is closer to 0 than it is to 1, quite a bit closer. So this is going to be very unlikely, but it's not impossible. Okay? So using this information, the probability being 1/40th, about how many would you expect to be defective in a shipment of 5,000 pairs of genes? Well, you could take the probability like we did previously and multiply 1/40th times 5,000. And I know that 40 goes into 5,000 125 times. So this is going to give me 125. And then if I wanted to, and what I think I'm more comfortable with is making a ratio box, we can go back to the total number defective the number defective out of the number total, and based on our simplified version of the story previously, I know that one pair of genes is defective out of every 40 pairs. So if 1 out of 40 is defective, and the total number that we're working with now is 5,000, to get from 40 to 5,000, I multiply by 125. And when I multiply by 125, 1 times 125 is 125. So in both ways, I find that the number of defective genes that I could expect in 5,000 pairs would be about 125. Still about 2.5%. So you may be wondering, well then what's the difference between theoretical probability and experimental probability? Experimental probability is the actual data that you get from performing trials over and over again. The theoretical probability is what you expect to happen based on the number of possible outcomes and then the outcomes that you're looking for. So the following data were gathered after 50 rolls of a 6-sided number cube, and these are the results. There were 10 ones, 4 twos, 8 threes, 11 fours, 8 fives, and 9 sixes for 50 rolls total. And the question says, find the probabilities of rolling an odd number. So 1, 3, or 5. I know that I rolled that die 10 times to get 1, 8 of the times I got a 3, and 8 of the times I got a 5. Those are the odd numbers. So 1s, 3s, and 5s. Now I know that I rolled them an even number of times, but that isn't what it's asking. I rolled an odd number, 1, 3, and 5. 10 times, 8 times, and 8 times. So the probability, if I'm working experimentally, the probability of getting an odd would be the number of times it occurred over the total number of trials. Well, I rolled the die 50 times. That's the total number of trials. And 10 plus 8 is 26. 26 out of 50 is going to give me about 52%. But theoretically, the probability of getting an odd number would be the number of favorable outcomes, so there are 3 odd numbers, out of the total number of possible outcomes, and there are 6 possible outcomes when I roll the 6-sided cube. So the probability that I should get an odd should be 3 out of 6, which is 1/2, which is 50%. You will notice that the experimental and theoretical probabilities are similar. Generally, they come out to be similar. So these are the results now, something completely different, of how many times you get a particular number when spinning a spinner. So just so we can read the graph accurately, the number of times I spun and got a 1 was 8 times. The number of times I spun and got a 2 was 6 times. And all in all, there were 50 times the spinner was spun. These are the results, okay? And the question asks us to use the bar graph to find the experimental probability of the given event. So spinning a 6, the total number of times that getting a 6 happened was 7 out of 50 total. 7/50ths cannot be simplified. I'm going to leave it as 7/50ths. How about spinning an even number? Well, a 2 was spun 6 times, a 4 was spun 11 times, and a 6 was spun 7 times. 6 plus 11 is 17, plus 7 is going to be 24. So 24 out of 50. If I simplify that, I can say 24 50ths is 12 25ths. That is going to be my probability of spinning an even number based on experiment. So 12 25ths. How about the probability, experimental probability of not spinning a 1? Well, not spinning a 1, well, spinning a 1 happened 8 times out of 50. So 50 minus 8 is 42. So 42 out of 50 is what has been observed of me not spinning a 1. 42 50ths can be simplified to 21 25ths. And 21 25ths is going to be our experimental probability of not spinning a 1. How about spinning less than a 3? That would be either spinning a 2 or a 1. And that happened 14 times. So 14 out of the 50 spins was less than a 3. To simplify that, I could divide them both by 2, giving me 7 25ths. 7 25ths is my experimental probability. How about spinning a 1 or a 3? Well, 1 happened 8 times, 3 happened 9 times, and so that's going to be 17 out of 50, which cannot be simplified. So my experimental probability is pretty much done. How about spinning a 7? Based on the numbers it's possible to spin, is it possible to spin a number greater than 6? No. So to spin a 7, spinning a 7 was observed 0 times out of 50, so we can say that the probability of experimental probability of spinning a 7 is 0. Lastly, to apply this, during a 24-hour period, the ratio of pop songs played to rap songs played on a radio station is 60 to 75. What is the experimental probability that the next song is rap? Well, keep in mind that the experimental probability is what you are measuring out of the total. Don't forget that it's out of the total. Because 60 to 75, if this is pop to rap, the total is going to be 135, not 75. So rap, again, this is pop to rap. So rap is 75 out of 135. And if I were to simplify that, let's see, divide by 5 and divide by 5. This gives me 15, 26, no, 27ths. So 15 out of 27 is the probability that the next song is rap. 15 27ths. Which is greater than or less than 50%? A little bit greater than, right? Okay. 15 27. I can actually simplify this further. I knew I could. If I divide them each by 3, I get 5/9. That looks better. So 5/9 is the probability that the next song will be rap. If 5/9 is rap, what's the probability the next song will be pop? Keep in mind that these need to add up to be 1. So if rap is 5/9, then the probability that pop will be played next, if those are the only two options, would be 4/9. This will come into play in example B. Out of the next 90 songs, so that's the next 90 songs total, how many do you expect to be pop? So we can use our pop probability and say, well, if 4 out of 9 are pop, so we can say pop out of total, 4 out of 9 are pop, so how many out of 90? Well, from 9 to 90, that's times 10. 4 times 10 is 40. So I would expect 40 out of the next 90 songs to be pop based on our experimental probability of this information.